This video is about conservation of energy and conservation of energy within a system. The first thing I want to talk about is ways that you can depict energy and energy conservation. So let's say I have a ball and it's moving up the hill. I pushed it and it slows down as it travels up the hill. So at the bottom of the hill, this ball has all kinetic energy. So if we think of this as a pie, think of the circle as a pie chart, we can see that this whole pie is kinetic energy. As the ball rolls up the hill, the kinetic energy will be converted into potential energy. And so partway up the hill, we'll have some kinetic energy and we'll have some potential energy. And that potential energy is going to be gravitational potential energy. And then once you get to the very top of the hill, the ball's no longer moving. And remember, kinetic energy is 1/2 mass velocity squared. And so if this ball has no velocity, it has no kinetic energy, meaning this whole pie has been converted to gravitational potential energy. Remember our units, the equation there is mgh, where you can find that by just looking at the height of the hill, or the height, the change in height. Here you have a very similar problem where you have, in this case, this is a wind-up toy and it's traveling up the hill. And so the rabbit starts with some small velocity, and then as it travels up the hill, it actually speeds up. And so what happens to the energy that's in this system? So at the beginning, let's say that this rabbit isn't moving at the beginning, and that this is the base of our hill. So this is our height of 0 meters. At the very beginning, at the base of this hill, this is a wind-up toy, and so all of the energy in this wind-up toy is stored in a spring. And so I'm going to call this US. You have all elastic potential energy at the beginning. As this rabbit moves up the hill, there's going to be less elastic potential energy. Maybe at point B, it's actually half of this pie is elastic potential energy. And then you have some of this is going to be kinetic energy, and some of it's going to be gravitational potential energy. Notice here I'm using UG to denote potential energy. You can also say PE, potential energy G. It's important to recognize both of these as ways to write potential energy. Then when this rabbit gets all the way to the top of the hill, we have maybe it's no elastic potential energy, or maybe it's just a teeny tiny sliver of elastic potential energy. And then both the kinetic energy has increased and the gravitational potential energy has increased. So PEG and KE. This is one way, these ideas of pie charts is one way to depict the amount of energy within a system. The other way to depict energy within a system is to use bar charts. I think that the bar chart is actually an easier way to talk about the amount of energy, because you can just talk about the number of boxes of energy, if you will. So starting out, it's all elastic potential energy, or 5 boxes of energy. Partway through, this is maybe I have now 2.5 boxes of elastic potential energy. I have half of my elastic potential energy, and then I have some sort of kinetic energy because it's moving, and some sort of gravitational potential energy. And then at the end, I have a very small amount of elastic potential energy, maybe less than a box, and then I have maybe 2 boxes, maybe 3 boxes of elastic potential energy, and maybe this much gravitational potential energy. So knowing that when you count this, that it all adds up to the amount of energy that you had in the beginning. These bar charts and pie charts can very easily now be converted into equations to talk about the conservation of energy. So we can say at point A, the energy at A is going to be equal to the energy at B, which is equal to the energy at C. If we wanted to relate the energy at A to the energy at point C, then we could write an equation that says that the elastic potential energy, given in this bar chart as EL, the elastic potential energy at A will equal the kinetic energy at C plus the gravitational potential energy at C plus the elastic potential energy at point C. Then we can go ahead and substitute in our equations. 1/2 k x squared at A equals 1/2 mv c squared plus mgh, where this would be the height of the hill, plus 1/2 k x squared xc. At this point, if you knew certain masses or you knew velocities or you knew the spring constant, you could solve for the one thing that you did not know. This energy equation is pretty easy when you have simple systems. When you have closed systems, meaning energy isn't flowing in or out of the system, this becomes a little bit more complicated once we have a open system that will take out energy from the system.